We've got this circuit with a battery and a resistor and an inductor. We're looking to see how much energy was delivered by the battery in the first 2 seconds, how much of that was stored in the inductor after that much time, and how much was lost by the resistor or dissipated in that much time as well. And that will give us a clue to what equation we want to use, because we should know that, power is going to be equal to the time derivative of the thermal energy that is lost and dissipated by these resistors. And should know that power is also equal to IV. And if we rearrange this by putting dt on this side, we could say that P dt equals d energy. And we'll just go ahead and integrate both sides, giving us this equation. So that's the kind of equation we're going to want to use to figure out what energy is being delivered and transferred and stuff here. The next thing we want to try to do is figure out what I might be equal to in terms of this, because we weren't given an I, but we should know that it's equal to epsilon over R, and then 1 minus E negative T, and then there's the inductor time constant thing there. This is all what we're going to start to plug into for this integral. We'll get the integral of epsilon over R, and then there's 1 minus E to the negative T over Ti, and then there should be a V in there somewhere, but it's the same as the epsilon here, so we're going to square that one. We got 2 epsilons, 2 V's. That's what the voltage is. This is over dt, and this is supposed to be equal to the energy, thermal energy. Now, some of these things are constant, so we can actually pull this out of the integral, and then we can just integrate whatever's inside of this. It shouldn't be too difficult. We'll basically end up getting a t, and then we'll go minus this will just remain the same. So we got e negative t over ti, but you've got something in the exponent here, so you want to divide this by negative 1 over ti. That's the derivative of what's in there. So this will transform into t plus, there's a ti on top here, ti, and then there's an e and a negative t over ti. So I'm just kind of trying to do this little integral in there. We still got this over on the left side though. So essentially we got e squared over r, and then we're not really done with this. We got t plus ti e to the negative t over ti. Just keeping in mind that this goes from 0 to 2 seconds. So now we can try to evaluate this little component here, putting in the 2 plus a ti e to the negative 2 over ti, and then we're going to have to subtract. If we plug in zeros here, we're just going to get minus ti again. Okay, and now multiply this by the e squared over r, and this should be equal to the energy that was delivered in the battery in the first 2 seconds. So let's go ahead and plug that all into the calculator. E squared is going to be 8 squared divided by r, 6.9. Then we can multiply this by 2 plus this ti thing is ti is supposed to be I over r. So we'll get 5 divided by 6.9, and then we'll multiply this by the e, and then there's going to be a negative 2 divided by 5 on top, and then we'll go 6.9 on the top there. And then we also have to subtract the ti, which is 5 divided by 6.9. And I think that was supposed to be multiplied by that. So we should get 12.26 or 12.25 in the first 2 seconds. 12.25 joules. Great. Now we can look at how much is stored in the inductor. And that one is going to be based off of U, like the UB thing. That's going to be equal to 1/2 inductance times I squared. The I squared, it's going to be this, like this thing right here. So if we were to square that, it will turn out to be something like this. We got 1/2 times the I, which is 5, times, we'll square this, being like 8 squared divided by R squared. And then we still have to multiply that by 1 minus e to the -2 divided by 5, put the 6.9 on top there. And this whole thing has to be squared. So I'll just make sure to multiply it by that, I guess. Let's get this going. So we have 2.95 joules stored in the inductor after 2 seconds. And so obviously the thing that was lost and dissipated by the resistor is going to be 12.25 minus 2.95. So 12.25 minus all that gives us 9.3 joules lost by the resistor during that charging time.